Hello everyone, this is Jim Corkins and we're continuing on with kinematics, and before we move on to two-dimensional motion, what we're going to do is we're going to review basically some trigonometry. So addition of vectors, basic addition of vectors as applied to motion, and we're also going to do some trigonometry review. And then we're going to try to put it all together before we move on to projectile motion. So if you haven't done the readings, please do so. If you have the Coletta textbook, do chapters 1, 2, and 3. If you are in Physics 111, that would be chapters 2 and 3 in the OpenStax book, and Physics 121, 2, 3, and 4 in OpenStax. Okay? All right. Well, we've been talking a little bit about vectors, and I'm sure you all know about the difference between vectors and scalars, but let's just get that straight right now. A vector basically has magnitude and direction, okay? So essentially, the scalar quantity is just the size of the vector, right? So you could just think it's just a magnitude. It's just a number. And we often have seen it as an absolute value. So I'm going to go to comments. I'm going to mark up this document. So you go to comments, and then it'll pop out this little arrow. You click on that arrow, and now you have more room. And here you have a bunch of tools. Now you can put text box in, really good tool. There's the drawing tool with pens. You can erase. You could put shapes in like arrows and vectors, which we're probably going to use. But right now I'm just going to mark up this document. We're going to talk about it. So we've always seen a scalar quantity with little absolute values. So let's say you have an initial velocity vector that is a positive 3 meters per second. Okay. So we've seen that. But the magnitude of this velocity vector, okay, is just the speed of this. So you're putting an absolute value around this, which means the speed of the object is just 3 meters per second. It's not positive 3 meters per second. It's not negative 3 meters per second. It's just 3 meters per second without a positive or negative in front. Okay, so it's a valueless. It has no direction to it. Okay, and so the absolute value is what describes the magnitude. Okay, the vector part, okay, so let's say this is 3 meters per second now, and this is the initial velocity vector, okay, and it's positive, so it would be pointed to the right. So now this thing has a magnitude of 3 meters per second, but also the positive indicates the direction, okay. So things that aren't vectors is something like mass, volume, speed, density, things like that. Things that do not, they're just basically, it's almost like descriptive statistics. However, things that do have a value to it, a vector, things that do have vectors are velocity, force, acceleration. We're going to get into momentum, and also impulse. Also, by the way, back to scalar stuff, mass, volume, speed, energy is a scalar quantity. So it has no value. Okay. So that's the difference between a vector and a scalar, and hope you've learned a little bit about what a vector is. So when you have more than two vectors, okay, when you have more than one vector, like two or more vectors, and you add them together or subtract them, okay, you get a resultant vector, okay. So a resultant vector is the resultant of the addition of subtraction or subtraction of two or more vectors, okay. So it's two or more vectors, okay. So if you have two vectors that don't act in the same or opposite directions, you have to use a parallelogram rule. But most of the time, especially in what we're going to be doing two vectors at right angles, right? So therefore, the length of the resultant vector is a relationship, is the square root of the length of one side plus the other side, right? So if you have an opposite or and an adjacent, okay, then you would square both of those and take the square root of the sum of that, and that would be the length of the hypotenuse. And the hypotenuse would be the resultant vector of addition of two vectors at right angles to each other. But if the two vectors don't act in the same or opposite direction, you have to use a parallelogram rule, and we will get into that a little bit. Okay. The formal method of vector addition is this. If you are given two vectors and they just call it vector A and vector B, really from the worksheets, the understood part is that this is positive A and this is positive B. Okay? So positive A is pointing up and to the right, and positive B is pointing down and to the right. So when you have to add these two vectors together, what you have to do is take the head of one and add it to the tail of another. So I'm going to take the head of A and add it to the tail of B, and now you get something like this, right? So the resultant vector of this is you started here, you walked up and to the right, down and to the right, and then you ended here. So the resultant vector always goes from where the start is to the ultimate end. It's a displacement vector, really. Okay, so you go from start to finish. Okay, so the resultant vector of A plus B is this, and in order to get that resultant vector, you get A squared plus B squared square root, as long as this was a 90-degree angle. Okay, so this is the basics of vector addition. All right. Again, you take the head of one vector and put it to the tail of the other, and then once you do that, then you identify the start and you identify the finish. Then the resultant vector goes from start to finish, and it doesn't matter the order in which you add the vectors as well. I just want to point out you don't have to add the head of A to the tail of B just because it's written out this way, right? A plus B equals B plus A, right? So you could take the head of the head of B, and add it to the tail of A, and so you started here, then you end here. So if you started here and then you ended right here, then that is the resultant vector, and that resultant vector would be B plus A, which is equal to A plus B, right? So see how this vector is the same as this one? Since I'm free drawing this, it's not the exact same size, but they are the same vectors. Okay? So it doesn't matter the order in which you do vector addition. You just have to follow the procedure. You take the tail of one and add it to the tip of another, and then the resultant vector goes from where you started to where it ended, right? You started here, up and to the right, down and to the right, you ended here. So you started here, you ended here, and that's the resultant vector. Okay? Well, let's do some practicing. But before we do that, real quick, I just wanted to say this real quick. Oftentimes, vectors are overall vectors are described as just the resultant vector themselves. So you'll be given a B vector, okay, and you'll be asked to break that up into its XY coordinates, okay. So it's X direction coordinates and Y direction coordinates. We're going to be doing that a lot, right? So if you have a coordinate system that is pointed up and down along the Y axis and left and right across the X axis, and you're given a vector that is pointing diagonal to those two axes, well, you're going to have to break that up. Most often than not, you're going to have to break that up into its x and y coordinates according to your coordinate system. So if you're given this b vector right here, what you're supposed to do is a procedure that I do is this. I just do some basic description of this, right? So which way is this b vector pointed in terms of up and down and left and right? Well, this vector is pointing up and left, right? Or you could say it's pointing left and up. All right. Well, do that basic description of that vector, and that is actually, you've described the component vectors. So you always start at the tail of the resultant vector that you're given. Okay, and since you started here, your only choice, well, you've got two choices. You could start with the upward vector here, the y component vector, and then you draw the x component vector here. And this would be bx. And it would be pointing to the left. Okay? Or you could start here and then go with your x component vector and then add the y component vector to it. And when you do that, what you've done is you've described this diagonal vector. And anytime you're given a diagonal vector, that is a resultant vector, or in other words, it's a hypotenuse, right? And so by breaking it up into its component vectors, so again, if you're given a hypotenuse or a diagonal vector like this, like the b vector, then you've got to do what is called decomposing, okay? So you've got to decompose the b vector here. And when you do that, you're breaking it up into components of the x-axis and y-axis, okay? So by decomposing the b vector, you're breaking it up into components that are parallel to the given axes, x and y. Axes, I think that's the plural component, the plural of axes. Anyways, so basically by decomposing this vector, you're breaking it up into its x direction and y direction vectors, okay? So we're going to be practicing that a lot too, okay? Well, let's do some practice. Let's just do some basic vector addition, okay? So here you have a p vector, which is pointing up and to the right, and it's a positive p vector. And then you have a positive q vector that is pointing down and to the right. Don't worry, down is negative, is pointing in the negative y direction. But if you have vectors that don't fit along an x or a y direction, just assume that they're positives, and then you could break it up into its basic. You could decompose these vectors and get the x direction and y direction stuff. But with basic vector addition, if you're given a vector called p and they don't say it's negative p, assume it's a positive p direction, okay, when it doesn't fit along any of the axes. Anyways, here we go. You've got a vector that is pointing up and to the right, and it's a positive p vector, and you have a positive q vector that's pointing down and to the right. What do you think is going to be the components, is going to be the resultant vector of the addition of p plus q? So go ahead and take a moment and free draw this. You could even use the vector parts. You could even use the vector tools right here to help you out. Okay? So try this out. Pause the video now. All right, well, we're back. Here we go. What I'm going to do is I'm going to take an arrow and I'm going to draw it, and I'm going to call that's going to be my P vector. Okay. And so what's great about the PDF stuff is I could overlay this vector right here, right on top of this, right? So the P vector is going to be red, and I'm going to make a Q vector that is going to be I'm going to give it a green color. I said green color. Oh, and you got to do borders. Okay, got it. You have to do the fill as well as this. Okay, so here we go. We have a Q vector and we have a P vector. We need to add them together. Okay, so one of the best things you could do, and we already practiced this, is you take the tip of one and you add it to the head of the other, right? And since I'm going to be doing P plus Q, I'm going to take the head of P, okay, head of P, and I'm going to add it to the tip of Q. All right. And now the resultant vector, which is going to be black, I'm going to draw from here to here, and so black will be my designated resultant vector. Okay, so if I add this resultant vector, and the resultant vector goes from start to finish. I'm going to move this out of the way so I can talk about this. So I started right here. Here's my start right here. I walked up and to the right, and then I walked down and to the right, and then I ended here. So the resultant vector goes from start to finish. So I'm going to take that, I'm going to take the tail of that, and then I'm going to stretch this out to the head of this. And so that is a resultant vector, and that is P plus Q. I'm going to call this P plus Q. All right, and I'm going to make that black. So that is the resultant vector, okay, which looks a lot like A. Well, some of you might not have done P plus Q. Some of you probably did something like Q plus P, which means you took the head of Q, green is Q, you took the head of Q and you added to the tail of P. Well, if you do that, so you started here, walked down and to the right, then you walked up and to the right. Well, that also results with the same thing, except this is not P plus Q, this is Q plus P, right? Which is equal to P plus Q. So I want to point that out, that those two things are equal, okay? And I gave it too much room here. So this is Q plus P, because this is Q and this is P, so Q plus P, but that's also equal to P plus Q. Either way, you get this vector that's pointing up and to the right, which is a lot like A. So hopefully you were able to circle this, and the answer to this is A. Come on. Okay, there we go. So the answer is A. Let's try another one, shall we? All right, here you're given P, which is pointed down and to the right, and you're given Q, which is just pointed to the left. And I know it sounds weird. A leftward pointed Q should be negative, but we're not working according to a coordinate system that's up and down and left and right. We're not decomposing these vectors. We're just doing vector addition. So there we go. This is pointed down and to the right, and this is up and to the left. Okay. I want you to go ahead and add those vectors together and then match that up into, well, which one of these choices, A, B, C, or D. Okay. So try that out now, please. Well, we're back. What I'm going to do is I'm going to use, again, P is going to be red. So I'm going to designate that as red. Let me change the color. I just want to make sure I get the magnitude correct, meaning the size of that vector. I want to get the same size. Okay. Which looks about right. If I get it a little, there you go. That looks perfect. So that's P. Okay. And then I'm going to add that, I'm going to add Q to that. So Q is another vector which is pointed just to the right. There we go. That is green, and the border is green. So this is Q. So I'm gonna, again, it doesn't matter the way that you do it. So let's put Q to the back of P. So let's put the head of Q to the tail of P. All right. Well, the resultant vector of that, so you started here, you walked just to the left, and then you walked down and to the right. Well, that resultant vector, again, which I'm going to use as black, is going to go from start to finish, and that will be, this will be the resultant vector. And again, it doesn't matter the order at which you do it. Because it ends up being the same whether you do P plus Q or Q plus P. Okay. So for example, notice that this PQ vector is now pointing down to the left, which would match up with A. All right. So this is, it would match with A. But let's just, again, I want to emphasize this. Let's make sure that that is the case. So if I grab this vector, the Q vector, and add it to the head of P, notice that the P plus Q vector ends up doing the same thing. Down and to the right, you started here, down and to the right, and then to the left, you ended here. The resultant vector goes from start to finish. And so, same thing. This is exact same thing. Okay? So let's do one last one, and this will be quicker. What I want you to go is, again, do vector addition. You've got the A vector, which is pointing up and to the right. So the A vector is pointing up and to the right. The B vector is pointing down and to the right. So go ahead and add those two vectors together, and let's see what you get. All right. I'm going to use red for the A vector in this case. And so the A vector is pointing up and to the right. And once I got that magnitude measured, I've got it here. And I'm going to just grab a B vector, and I'm going to measure that B vector out. And I measured it out, and there you go. Can you see the resultant vector? Okay, so the resultant vector is going to be a black arrow. Oops. The resultant vector, I'm going to use black. and it started here at the tail of the red vector or A vector, and it ends at the tip of the green vector. You started here, you ended here, so that's the resultant vector. And so this is A plus B, or B plus A, and so what does that look like? Well, that looks a lot like C. All right, I hope you learned a lot about vector addition. Let's move on, and we're moving on to vector subtraction, okay? So vector subtraction varies, it's the same process, except you're going to add a step before you do the vector addition, right? So if you're given a vector that's pointed up and to the right, and that's going to be positive A, and you're given another vector, B, which is actually positive B, well, there you go. But if you need to subtract B from A, all right, so you're going to, so if positive B is pointing down and to the right, well then up and to the left is going to be the negative B vector, right? Correct? So if down and to the right is positive B, well then the opposite of that has to be negative B, all right? So now you're going to go ahead and add those two vectors together. You have a positive A and then a negative B vector, which is what they did. They've taken the tail head of A and added it to the tail of the negative B vector. And then the resultant vector is you started here, and then you ended here. You walked up and to the right, up and to the left, ended here. So then the resultant vector always goes from start to finish. And so this is the addition of A and negative B. So this would be the A negative B vector addition. Negative B. There you go. And so that's what they're showing. So what you have to do is, if you're given a positive A vector and a positive B vector, and you have to subtract the B vector, you just reverse the direction of that B vector, and then you just go through the vector addition process. Okay? So we're going to do two examples. Well, we'll do two examples in a second. I just want to emphasize something here, that if you need to, again, reversing a vector, if this vector is pointing up and to the right, then the reversing of that vector is going to be pointing down and to the left. So again, this is just the same process that we saw before up here, but it's just shown in a different way. Okay, so I want to give you two examples of the same thing, so to better reach the audience here. Okay, so if the B vector is pointing up and to the right, then the negative B vector has to be parallel to that and just pointed the opposite direction. So you're just kind of taking the tip of this vector and then adding it to the bottom, and then that would be the negative B. Okay, so let's do practice. And again, here's our P and Q vectors. What I want you to do is I want you to subtract Q from P and then go ahead and do that vector addition. Okay, so try that now and hit pause. Okay, we are back. So what I want you to do, so what we're going to do is we're presented with a positive P and we're presented with a positive Q vector. Okay, so now what we're going to have is a positive P vector minus the Q vector. Okay, so that means we need to reverse the Q vector. All right, so what I'm going to do, again, I'm going to use red for, I'm going to use black for the handwriting part, but I'm going to use red for the vector head. And I'm going to measure out the P vector. So this P vector is pointing up and to the right, and it is going to be red. There we go. So I have that measured out. The Q vector so the positive Q vector is pointing down and to the right. correct? But what we need is a negative q vector. So that means we need to reverse this. So now the q vector is going to be pointing up and to the left. So again, it doesn't matter the order at which you do this vector addition. You just have to take the head of one and put it to the tail of other. Well, I'm going to take the head of p and put it to the tail of q. Okay, of the negative q vector, I should say. So this is negative q. And this is positive p. Well, now that we have that aligned, let's do the resultant vector. The resultant vector, which again I use black for the resultant vector, is going to go from the where you started the journey. So where I started the journey was right there at the bottom of the p vector. Okay, so I started right here, I ended right here. So I'm going to take this, stretch it all the way to the tip, and then I'm going to kind of align it a little bit better. So now what I have is positive p minus q. And that is going to be the resultant vector of p minus q, of the resultant of p, positive p and negative q. Okay? Sure that's a little bit more measured out. So again, all I did is I was given positive p and positive q, and I just reversed the q vector. And then when I did that, then you just do the vector addition process, and then you figure out your resultant vector. It goes from start. So I started here, I ended up here on the top left. Okay, so this black arrow looks a lot like B. So this is our answer to this. Okay, how'd you do on that? Let's do a similar one, but this one, what we're going to do is we're going to do q minus p. All right. So, well, is p minus q equal to q minus p? If it is, then the answer will be B again. So what do you think it is? So go through the process, practice the process, and what I want you to do is try it out and see what you get. Okay? Pause the video now. Okay, we're back. Well, I am going to, again, I'm going to do the p vector, which is red. I'm going to start with that. The positive p vector is pointed up and to the right, so we need to make it a negative p vector. And what we do is reverse it. It's got to be exactly parallel to it and the same magnitude, but just opposite the direction. So here is our negative p vector. Okay? And I'm going to, again, this is our negative p vector. Okay? Well, let's measure out our positive q vector, and in this case our positive q vector is going to not be reversed because we're doing q minus p. So we're going to leave this as a positive q vector. Okay. So what I'm going to do is I'm going to add this q vector, this positive q vector, to the tail of the p vector. Okay, so this is positive q. All right. Well, now we started here and we ended here. Well, let's go ahead and figure out the resultant vector. Which way do you think it's pointed? Well, you started there, ended here. I'm going to make that black because that's what I use, the color I use for resultant vectors. And it's pointing exactly straight down. So so the answer here is going to be C. So I had asked before, is P minus Q equal to Q minus P? And it is not, actually. It's the opposite direction. It looks like it's the same magnitude, but just opposite directions. So that's kind of cool. That kind of makes sense, right? If you have P minus Q and you multiply through by a -1, you get Q minus P. So the negative of the resultant vector will be Q minus P. So the negative of P minus Q is going to be Q minus P. So it's just reverse that. So pretty cool. I hope you learned something. Now what I want you to do is do a leap in logic and see if you could try this by yourself. So what I want you to do is do a vector addition, but I want you to do a vector addition of two A vectors and then a negative B vector. So you're given a positive A vector is pointing up and to the right, and a positive B vector is pointing down and to the right. And I want you to perform this operation. So I want you to give me the resultant vector of 2A minus B. So let's see you try this on your own and see if you can kind of figure it out. And then what we'll do is we'll work on it together. And then we'll do a practice one on another one, and I bet you'll do a lot better. So go ahead and try this on your own. And pause the video now, and we'll do this together afterwards. Okay, we are back. So the A vector I am going to use as red. Okay, so I'm going to try to line this up, and I'm going to use it as red. And really, this is the 1A vector. This is actually a positive 1A, right? So this red vector is a positive red vector, okay? It's a positive 1A red vector. Well, if you think about it, to get a 2A vector, you could double the size of this vector, or what you could do is just double the vector itself, and so I just copied and pasted that, and now I have a 2A vector here. So this is a positive 1A vector that I've just doubled right there. And so I have a positive 1A vector and another positive 1A vector. Well, isn't that just a 2A vector, right? So wouldn't that just be a 2A vector? So there you go. That makes sense. All right. Well, now we have to do the negative B vector. Well, here we have a B vector that is pointing, a positive B vector is pointing down and to the right. And I'm going to use green again for that. All right. So here's our negative, this is our positive B vector. Well, to reverse that, I need to make it up and to the left. And I'm just going to measure out to make sure I have the length of this, or magnitude, correct. And that looks like that. And again, the process doesn't matter where you place it as long as it's tip to tail. So I'm going to add it to right here. And so this green vector is the negative Q vector, or negative 1Q vector, I should say, since we're now talking about multiples of vectors. Okay. Well, then the resultant, again, you will go from start to finish. So it doesn't matter the order in which you do this. Again, I could have taken this and brought it up here, and you'd get the same thing as we've seen before. But I started here, at the tail of the -1 Q vector. I walked up and to the left, and then I walked a large distance up and to the right, so I ended here. Okay, so now the resultant vector, which I'm going to make black, is going to go from start to finish. Okay, and this is going to be positive 2a minus q. So this is our resultant vector. And that looks a lot like a to me. So this is the same thing. All right. How'd you do on that? So what you were supposed to learn is that you have to take these vectors and then how to actually perform an operation on vectors. And this would be performing an algebraic vector operation on vectors, and then you do a graphical analysis, right? So, so vector addition is a combination of graphical analysis, but also algebraic operations. Okay. I just want to add something really quick to add some depth to this. If I had used this component here, and I could add this in any way I want to, if I added the 1a vector right here, and then let's say I wanted to add the -q vector here. So this is the -q vector here, and then add another positive 1a vector here. Well, the cool thing is, again, it doesn't matter the order in which you do it, because that would give you the same result. Okay? So you could even take the components of the 2a, you know, the single 1a vectors, and then add them together in whatever order you want, and then put that here. So this is kind of like the addition of multiple vectors at the same time. So that's going to be leading into another thing. Well, let's try another problem. What I want you to do is again you're given positive a and positive b. What I want you to do is go ahead and do -2a minus b. So now you're going to have to do a lot more. So perform these operations on these vectors, and then go ahead and find this result graphically. Right? So perform this algebraic operation on these vectors, and then do the graphical analysis, and then solve the problem, please. Pause now. All right. Well, we're back. Here we go. Again, I'm going to measure out an a vector, but that would be a positive a vector, and I'm doing it partially so I could set the color. Okay. Well, that's the positive a vector is pointing up and to the right. We need a negative a, so it needs to be pointing the exact opposite of that. Okay. So that looks like it's this. So this is a negative a vector. Okay. And in fact, a -1a vector. Okay. And just like before, you could make two of these. So making two of those is equal to -2a. All right. Well, let's do the b vector. The b vector, which should be negative, is going to be pointing up and to the left, and that is green. So that is going to be green. Okay. And so that is pointing up and to the left, and we've got to take that and add the tip of that to the tail of the others. That's the B vector. Okay. And it doesn't matter the order in which you do it. Right? We could have, in fact, let's do it out of order. This is a negative B vector. Let's do it out of order this time. Make it kind of fun. Okay, so you've got all those vectors right there. And now the resultant vector, again, I'm going to use black for that. That is going to go from the very beginning of the journey to the very end of the journey. So my journey began right here. So this is the beginning. This is start right there. And here's the end right here. Okay, so I've got to take this resultant vector right here. I'm going to stretch it to the end and put it right at the beginning, right there. So that is the resultant vector, and that is negative 2a plus b, negative 2a minus b. Okay. Again, it doesn't matter the order in which you do it. Watch. I'm going to move the negative 1a vector over there, and move the so I'm moving the negative 1a vector over there and adding it to the other 1a vector, and taking the negative b vector, negative 1b vector, and doing it that, and you get the same result. So it doesn't matter the order at which you add vectors, just as long as you perform the operation first and then you do your vectors. So perform the operation on your vectors. Perform your algebraic operation on your vectors, and then do the vector analysis. Okay? So that looks like it's pointing down and to the right, and so this looks really close to A. So our answer to here is A. So that's pretty cool. All right. So we kind of talked about this a little bit. So now let's take component vectors. Okay. So if we have a vector F1 and we have a vector F2, really, if you broke that up into their component vectors, you would have so F1 would be pointing, so that vector is pointing up and to the right. So I'm going to decompose F1. And so when you do that, you get its component vectors, and it's pointed to the right and also pointed up. It doesn't matter the order in which you do that, right? Correct? Right? So that F1 is pointing up and to the right. And then I'm going to also say, so now you're going to add F1 to F2, right? Well, if you decompose F2, I shouldn't add that. If this is a component and you have an actual coordinate system, you can't call this positive F1. You have to decompose it and then label the parts that are aligned to your coordinate system as that. So anyways, F2, if you decompose F2 into its component vectors, you would get a really long vector up and a short vector to the right. That is an up and to the right vector. Well, if you do this, again, it doesn't matter the order in which you do this, you add up the component vectors, the decomposed vectors of F1 and F2, and it ends up with the same result as the vector addition of F1 and F2. Okay? So we could have taken these vectors right there and decomposed these into a positive qx vector and a negative qy vector, and it would have added up, and then a positive p vector and a positive px vector and a positive py vector, and decompose these vectors into the component vectors, added them together, and it would have resulted in the same thing. Okay? So this is saying the same thing, but you could do this. Now, why is this important? Well, now we could actually apply this vector addition stuff to to velocity vectors, right? So velocity vectors and acceleration vectors and also displacement vectors, well, they're just vectors, right? Well, you can apply this to what we've learned, okay? So if you have an object that had a positive velocity vector up and to the right of 4.5 meters per second, okay, so that's it. So it was something up and to the right at a 45-degree angle at 4.5 meters per second. Well, the Vx part of that, okay, is 4.5 cosine of 45 degrees, and the Vy part, and we'll get into that in a little bit. The Vy part is going to be 4.5 sine of 45 degrees, because the Vy is opposite the angle, right? This side is opposite the angle, and this side is adjacent to it. Okay. Well, we've broken that up into its component. We've decomposed it into its component vectors. Well, now you have a V3 vector that is going to be down and to the left. Okay. That is down to the left. So Y3 is going to be, well, this is opposite the angle 30 degrees. So this is going to be 9 meters per second sine of 30 degrees. And this, suppose I should write this down. This is going to be 9 meters per second sine of 30 degrees. And it'll be negative. It'll be pointing down. This side is adjacent to the 30-degree angle. So Vx3 is going to be 9 meters per second in the negative x direction, cosine of 30 degrees. I said this one before. This is going to be pointed to the right, 4.5 meters per second, sine, cosine of 45 degrees. And this is going to be positive 4.5 because it's pointed up at sine of 45 degrees, right? Well, and we have a V2 vector that is only pointed up. So V2 is only pointed up in the positive y direction, and it has no components in the x direction. Well, you add all those component vectors up, right? So if you add up and to the right, actually, I'm going to try to use this to emphasize this. So I'm going to use up and to the right, and this is pink, correct? So I just did the 4.5 meters per second up and to the right. Now I'm going to do this purpley vector, draw another vector down and to the right, and that is kind of purpley. So I'm going to grab that guy right there. I'm going to add, well, that's going to be kind of weird. So that's the purpley vector. Okay, and then I have a blue vector pointed straight up, which is the V2 vector, which is pointed straight up, and that looks like it's baby blue. Okay, well, if you add these vectors together, you should get a resultant vector. And the resultant vector, okay, and it doesn't matter the order in which you add these guys, so I'm going to try to do it this way. So let me label this pink guy, which is a 4.5 meters per second vector. This one is the 5 meters per second baby blue vector. And this purple one is 9 meters per second. Okay, well, if I add that, okay, the resultant vector is going to be the resultant of all this stuff. Okay? and that is black. So so I started here, I walked up and to the right, then straight up, and then down and to the right. Well, the resultant vector is going to be from start to finish, and that'll be black. And so this is going to be the addition of all of those, right? Which is the same thing that we get here, right? Well, how do I know the length of this, right? Well, what you have to do is you have to decompose these vectors, the 9 meters per second, the 4.5 vectors, into its base components according to the coordinate system. And then you do, basically add the, what you're going to do is you're going to end up creating a really big triangle. Okay. So what I'm going to do is I'm going to break up this guy here into his. You want to make a really big right triangle. So I'm going to take this vector right here, and then I'm going to add it to this vector right here. So it would be 4.5 meters per second cosine, positive 4.5 minus this. So I could, and when you do that, what you would get is you would get a vector just to the left. So by adding these two x direction vectors, you would get just a vector to the left. And so I don't know what negative 9 meters per second sine of 30 degrees is, but the difference between that and this so this right here, so the resultant of that is going to be, so that is being subtracted off. What I'm going to do is take this, and now the resultant of negative 9 meters per second cosine of 30 degrees plus 4.5 meters per second cosine of 45 degrees is this part right here. And so that's what they're talking about right there. And then you do the same thing with the down vectors. You have two up vectors, positive 4.5 sine of 45 degrees, that you're going to be adding to 5 meters per second right there, which now I'm going to elongate that, so I've added that. And then you've got to subtract off from this. So I'm going to take that, and so the up vector is bigger than the small vector, the down vector, so I'm going to subtract that off. So the resultant will look like this, and that is the upward portion. I probably made a mistake when I was doing that. And so that is a resultant vector. The y component is a resultant vector of this plus this, the vy1, vy2, and the vy3 vector. You add all those up and you get a vector this size, right? And so we by breaking them up, decomposing these v1, v2, and v3 into, by decomposing them into their component vectors, you get a resultant vector that is equal to the addition of all those vectors. And to get its length, you then do the addition of these vectors in the x direction, addition of the vectors in the y direction, and then you could apply, then you've created a right triangle like you could see right here, and then you could apply Pythagorean's theorem. Okay? A little complicated, but kind of cool. It's cool how you could kind of use algebraic manipulation and vector addition to actually get a resultant vector. And this is what pilots have to do all the time. And this is what, you know, plane pilots, but also pilots of barges and ships on the ocean. Okay, it's all vector addition. Well, let's do an example and try to apply it into our case. Carolyn is driving a car north at 30 kilometers an hour for 1 hour. All right. So she's driving 30 kilometers an hour for 1 hour. So how far has Carol driven? Well, that would be, what is that? 30 kilometers per hour. So velocity is equal to displacement In this case, it's in the y direction over time. So she drove north, which would be up, positive v, over a period of an hour. So she drove up at 30 kilometers per hour for 1 hour. And that's positive. So that means she went upwards 30 kilometers. Okay? So we have Carol who's going to be driving upwards 30 kilometers. So that was her displacement in that direction. Okay. She then drives eastward. Never eat sour watermelons. So I'm going to put a cardinal coordinate system. This is north, east, south, and then west. So she now drives eastward 60 kilometers an hour for 2 hours. So she's driving 60 kilometers an hour, and so this way she's driving in the positive x direction, delta x over delta t. So she's driving in the positive x direction, so her delta x is going to be positive vx delta t. So her displacement in the x direction is going to be to the right, 60 kilometers per hour for 2 hours. So that is going to be eastward, or to the right, at, it looks 60 times 2, 120 kilometers. The hours cancel out, right? So now she drives 60 kilometers, so that's going to be, and she drives 2 of those vectors to the right. So this is 60 kilometers plus 60 kilometers, and that's 2 hours. Okay. And then she's going to drive north again at 50 kilometers over 1 hour. Well, so now she's driving in the y direction. So Vy is going to be equal to delta, and I should have put a y on this. Right? So we're assigning directions to our velocities now with a subscript. Delta t. And it's upwards, so it'll be a positive there. So she's driving northwards or upwards at a positive Vy delta t. So she's driving 50 kilometers per hour for 1 hour. Okay, which means that she's driving upwards 50 kilometers. So now I'm going to try to do my best to, so I'm going to call that 50 kilometers, right? So that means she started here, she ended here, and she drove this distance all the way up and to the right. Well, another thing that we could do, and I'm going to go on to the next page, we could just add 30 kilometers to 50 kilometers for the y direction, and add 60 kilometers to 60 kilometers in the x direction. So what we could do is do this, 30 kilometers plus 50 kilometers, and that's a little bit bigger than I wanted, 50 kilometers, and we're going to add to that this 260 kilometers, guys. If we align them, what you get is a nice clean triangle, right? And notice that this resultant vector here is the same resultant vector that we did over here when we added the components as written by the story, right? Well, if you get that, well, now we could apply Pythagorean's theorem to find out how far what her net displacement is. And her net displacement would be from the start to the finish. So her net displacement is that big long vector. Well, now we have it here. In this form, we can't really figure it out. But in this form, since we made a right triangle, now we could apply Pythagorean's theorem. And so this side here, this is going to be the C side. Actually, I'm going to call it the hypotenuse. So this is the hypotenuse. It's equal to this side here, which is going to be 50 plus 30. So that's 80 kilometers. And we're going to square that. Plus 60 plus 60 is going to be 120 kilometers. And we're going to square that and take the square root of that. C squared equals A squared plus B squared, or hypotenuse equals opposite squared over adjacent squared, right? So what is that? Let's try to figure it out. I'm going to pop up my little calculator here and go 120 times 120 equals, so 1440 plus 80 times 80, that's 80 squared, is 2,800, and then I'm going to take the square root of this. So I'm going to take the square root of that. So this is 144. It was about 12 times 12, so 144.22. So this displacement, her total displacement from beginning end, should be 144.22 kilometers. Okay, and that's exactly what they're doing here, aligning them. So there we go. And they also want to know what this angle is too. They want to know what this angle is. Well, in order to get that angle here, we have theta. We also now have the hypotenuse, so we could use sine, cosine, or tangent, but I like to use what we're given. Tangent of theta is going to be equal to opposite over adjacent, correct? And opposite is 80 kilometers, right? 30 plus 50 divided by 60 plus 60, which is 120 kilometers. So the theta, you take the inverse tangent of theta, and that's equal to 80 divided by 120. And so let's see what we get here. Let's try this again. So this is going to be 80 divided by 120 equals, and then I'm going to go to trigonometry, tangent, whoops, I should have probably already had that set up. Let's try this again. 80 divided by 120. I guess on this I have to hit second function. Of this, and second function tangent. So it looks like this angle here is going to be, that can't be right. Let me try that again. 80 divided by 120 equals, okay, and now I'm going to do that. Second function tangent. 33.69 degrees. I didn't think it was 89 degrees. 33.69 degrees. Because that just, by looking at it, doesn't look like it's even close to 89 degrees. It'd be huge. It'd be way up here, right? It'd almost be vertical. It actually would be pretty much vertical. Anyways, so I had done a minor error there, but I caught it, luckily. So 33.69. So the distance she drove was 144.22 kilometers, but she also drove, the overall resultant vector angle is at 33.69. Or 34 degrees, right? And to the north. Okay? So now you could go on and do your lecture tutorials. Okay, so this first lecture tutorial let's just do one of them, is kind of like what we first were doing. When you're given an A vector and a B vector, assume that they're positives. So I'm going to put little positives on each one of these. You know, regardless of there's no coordinate system here right now. We haven't decomposed these vectors. These are the major vectors, right? So these are, you're all given the positive A vectors, okay? So that what Mark Summers wants you to do is he wants you to go ahead and assume these are the positive directions of these, and he wants you to perform this operation on them and then give you, in this case, the C vector. Give you the one vector that you're missing. All right? So in this first one, I have an A vector, positive A vector pointed down, and I have a positive B vector pointed to the left. So the positive A vector is pointing down 1, 2, 3, 4, 5, and 6. You have to count the head. So it's pointing down 6 units. And the positive B vector is pointing to the left 1, 2, 3, 4. Okay? So you're going to add, so it looks like we need to get the C vector from this. You need to get the one vector that you're missing. Well, we're missing C. And he's saying C is equal to the A vector plus the B vector. So you get it, again, you could do this in any way you want. I'm going to take that B vector and add it to the A vector. Or I could take it, the A vector and add it to the B vector, but I'm going to do it in this case. So I want to 1, 2, 3, 4. So there's 4 units to the right, 4 units to the left. So this is the positive B vector, which is 4 units. So that means the C vector is going to be starting here and ending here. So this is going to be my C vector. That is going to be my C vector. All right. What I want you to do is actually give me that length too. Okay. I want you to give me that length. So C vector is going to be equal to the square root of 4 squared plus 6 squared. If you add these vectors together correctly, and he's only giving you vectors up and down and left and right-ish, up and down, left and right, then you could, you're going to form a right triangle, and then you could actually give me that component. So in this case, that's going to be, what is it, 16 plus 36? And then we're going to do square root of that, 7.21. So this is going to be pointing down and to the right, 7.21 units. All right, so that's how you do that one. Sometimes he's going to give you something like this. He's going to give you the A and B vector, and you have to find the C vector. But he gives it to you where he's giving you a formula. So what you have to do is an algebraic manipulation, right? So if you need to find C, because you're missing C, you have to find C. What you're going to have to do is do the A vector and then take the B onto the other side. So I'm going to subtract that to the other side. So in order to find the C vector, I have to reverse the B vector. So the B vector was pointing up 6 units. Now it needs to be pointing down 6 units, right? So this is now the negative B vector, which is pointing down 6 units. The A vector is pointing to the right by 2 units. So I'm going to take that A vector, bring it over here. And that's a positive A vector. Well, the C vector will then go from start to finish. Okay, so that's the C vector, and that is going to be, this is going to be negative 6 units, really. So it's going to be negative 6 squared, which is going to be 36, plus 2, which are going to be squared. Okay, so that's going to be 4. So 36 plus 4, so we need to find the square root of 40. Which is 6.32. So C is going to be pointing down and to the right, 6.32 units. So this tutorial, I want you to try that. I want you to do these operations, okay? And this is your introduction to vector addition. Bye.